Okay, so let's get started. Good morning, everyone. Welcome to virtually to the Niels Bohr Institute. My name is Joachim Kopp. I'm based at CERN and have a dual appointment with Johannes Gutenberg-Universität in Mainz, Germany. And yeah, one of my main research topics is theoretical neutrino physics. I was very delighted to be invited to talk to you here about theoretical neutrino physics. These are going to be 3 lectures. The first 2 lectures are going to be more Blackboard style with only a few slides at the end. The third lecture is going to be all slides. So today we are going to talk about mostly about neutrino masses. So how do neutrinos get their mass? How is that developed theoretically? And then in particular also, how do we measure neutrino masses? Or how do we hope to measure neutrino masses in the future? Then the second lecture on Wednesday will be devoted entirely to neutrino oscillation, so the periodic conversion from one neutrino flavor into the others as they propagate. And finally, on Thursday, we're going to go a bit beyond the standard model, and we're going to talk about the possibility that there's more than 3 neutrino flavors in nature, and we're going to discuss some of the implications of that. So what I'm not going to cover in this lecture is, of course, theoretical neutrino astrophysics and neutrino cosmology, because on that you're going to have dedicated lectures by the experts. Right. If there are questions during the lecture, please just unmute yourself and interrupt me anytime. And other than that, I'm also available to answer questions on Slack or on GatherTown if we meet there. Okay, so the notes that I'm going to take here are going to be uploaded to Indico after the lecture as well. What is already on Indico now is the slides that I'm going to show towards the end of the lecture, and a longer series of lecture notes on neutrino physics. These are the lecture notes I usually use when I give whole semester courses on the topic. And here in these lectures here, we're going to draw some excerpts from those notes. But as I said, what I'm going to write here on my tablet is going to be uploaded to the Indico page as well after the lecture. Okay. So let's get started. As I indicated, we're going to start by talking about neutrinos and their masses. So that's section 1, neutrinos and their masses. I think the good thing about online lectures is that you can that one can blame illegible handwriting on the technology rather than on oneself. So I apologize if anything is illegible. Please stop me immediately, and I'll try to improve. So we're going to talk about neutrinos and their We're going to talk about neutrinos and their masses. And in this context, let's start by reviewing where neutrinos are in the standard model. So neutrinos in the standard model. Well, you know that the particle structure of the standard model consists of quarks and leptons and bosons. The quarks are the up, down, charm, strange, top, bottom. The charged leptons are the E, the electron, the muon, and the tau, and each of those has a neutrino partner, nu E, nu mu, nu tau. And in principle, I should have put the neutrinos on top of the charged leptons because that's how they end up in the SU2 multiplets. You also know how neutrinos are produced. So typically they are produced in nuclear reactions. This can be nuclear beta decays, or these can be higher energy reactions like pion decays, for instance. So produced in nuclear reactions, such as, let's say, for instance, pi plus going to mu plus a muon neutrino. What's important is that neutrinos are always produced together with a charged lepton, or they are produced in pairs, but in practice of most relevance are the processes in which they are produced together with a charged lepton. And the neutrino flavor is defined by the charged lepton with which a neutrino is produced. So the object that we call a muon neutrino is by definition the type of neutrino that is produced together with a muon. What we call an electron neutrino is the particle that is produced together with an electron, and so on. So why do we study neutrinos? Well, one reason is that by studying the flavor structure of the standard model, so how particles mix with each other, we hope to understand why the standard model has this particular structure. So, I mean, this structure with 3 families of particles, and each family containing 2 quarks, 2 leptons, it smells like there's a reason for it, right? It smells a bit like the way the periodic table of the elements looked like in the end of the 19th century, when scientists had discovered that there were chemical elements that were behaving in similar ways, but we didn't understand why. So we didn't understand the structure yet. That only came much later when we understood how atoms, what atoms are made up of and what the structure of atoms is. And somehow the flavor structure of the standard model smells similar. So the hope is that by studying neutrinos, we will be able to elucidate the origin of flavor. So may help elucidate origin of flavor. They may be able to help explain the baryon asymmetry of the universe. I assume you're going to hear about that in the lectures on neutrino cosmology, about the leptogenesis mechanism. So may help explain baryon asymmetry. So the fact that there is more matter than antimatter in the universe, one of the big unsolved problems in cosmology. And in fact, neutrinos may be playing quite an important role in this question. Finally, neutrinos may be able to teach us about dark matter. May teach us about DM. Either heavy partners of the neutrinos could be the dark matter itself, or at least the way the dark matter is coupled to the standard model could have to do with neutrinos. So we might be able to use neutrinos as messengers of dark matter annihilation, for instance. And there's many other virtues of neutrinos. Now, formally, the Lagrangian of the standard model, or the relevant part to neutrino physics of the Lagrangian of the standard model, has this structure. There is a sum over the 3 neutrino flavors, alpha equal E, mu, tau. So we conventionally use Greek indices to denote neutrino flavors. Then, of course, each neutrino has a kinetic term that has this structure, nu A bar L, I, D slash, nu alpha L. So just a regular fermion kinetic term. Note that I'm here introducing only the left-handed component of the neutrino. In the pure standard model, there's only left-handed neutrinos. So the neutrinos are just left-handed Weil fermions. Once they have mass, of course, we will need right-handed neutrinos, but we'll come to that in a moment. Then the neutrinos have the coupling to the W bosons. It comes with the weak coupling constant G divided by square root 2 times the W boson, W mu, times nu alpha L bar, gamma mu, and then the charged lepton of flavor alpha coupled to it, plus Hermitian conjugate. So there's, of course, the same coupling of the antiparticles to the W minus boson. And finally, there's the coupling to the neutral currents in the standard model. That comes again with the weak coupling constant, but this time divided by 2 times cosine of the Weinberg angle. There is the Z boson field, which carries a Lorentz index, and once again, nu alpha L bar, gamma mu, nu alpha L. And finally, all the things here are still under the sum. And then there needs to be a neutrino mass term. That's going to be what we're going to talk about in a moment. So notice that because of this structure, there's only left-handed fields appearing here. So here's the left-handed kinetic term. Here, the weak interaction couples only to left-handed fields, and the Z also couples only to left-handed neutrinos. So at this level, it's really sufficient to have only left-handed neutrinos. But as I said, once we introduce a mass term, we need right-handed neutrinos. Now, graphically, what I've just written down here corresponds to the following diagram. There can be a diagram with a W boson. Like this, for instance, a W coupling to a neutrino and a charged lepton, or a Z boson coupling to two neutrino fields. So let's say, for instance, a new alpha bar, a new alpha. That here is the Z mu. Okay, now let's talk about this mass term. In fact, there's different ways of introducing mass terms in neutrino physics. The simplest one is to just follow what we know about the mass terms of the other standard model fermions, the quarks and the charged leptons. That's what's called a Dirac mass term, after Paul-Adrien Maurice Dirac, who was probably on the picture that we saw in the introduction. So a Dirac mass term. The idea here is, well, we introduce a right-handed neutrino, so we augment the neutrino fields from Weil fermions to Dirac fermions. So they now have 4 components, and we can then write down a mass term that couples the left-handed components of the spinor to the right-handed components. So let's say in the standard model, without neutrino masses, only left-handed new fields appear. So we can, for instance, write the left-handed neutrino as 1 minus gamma 5 over 2, so the left-handed projection operator, times a 4-component field. And whatever that 4-component field is, this left-handed projector projects out just the upper 2 components. Let's call them chi1, chi2. And the lower 2 components are just unphysical. They don't appear in the Lagrangian. Now, a Dirac mass term makes these lower components physical. So a Dirac mass term makes nu right equal to 1 plus gamma 5 over 2 physical. So that's now the times nu physical. So that's now the projection operator that projects out the bottom 2 components of the field. So what does the Dirac mass term look like? It has this structure. There's a sum over flavors, this time over 2 flavor indices, alpha and beta. And there is a coupling M alpha beta, that's of course the mass. Then we couple a left-handed neutrino field to a right-handed neutrino field, possibly of a different flavor. And there is of course also the Hermitian conjugate. So we now have couplings of every left-handed neutrino flavor to every right-handed neutrino flavor. So these M alpha beta, they form a matrix, and this matrix can in general be off diagonal. What this means is that an electron neutrino or a mu neutrino are not states that have a definite mass. They are coupled to this through this matrix, and if I diagonalize the matrix, then the basis in which the matrix is diagonal is not the basis of flavor. So the particles that have definite mass are not identical to the particles that appear in the weak interaction. They are superpositions of the fields that appear in the weak interaction. And that will be very important in tomorrow's lecture when we talk about neutrino mixing and oscillations. What's also interesting is now, instead of 2 neutrino degrees of freedom, namely left-handed neutrino and its antiparticle, we now have 4 degrees of freedom, namely the 4 components of the spinor, the left-handed and the right components. So we now have 4 physical degrees of freedom. So in a sense, we have introduced new, new states at least. It's difficult to say whether we should say new particles, but at least we have introduced new states. And this is why sometimes people say that neutrino masses are already physics beyond the standard model, because it requires introducing new states that did not appear in the standard model. Now, there's one nice, more intuitive picture to understand why there are 4 degrees of freedom. And to understand this, look at the following. So let's assume we have here a neutrino, and the neutrino is moving in some direction with a momentum p. And let's also assume that the neutrino has a spin, and that spin, let that spin be anti-aligned with the momentum. So let's draw here an arrow that indicates the spin. Now, if the neutrino is massive, then I can, in principle, boost myself into a reference frame that is moving so fast that the direction of the momentum vector gets reversed. I cannot do this if neutrinos are massless, because then they are moving at the speed of light, and I can't have a reference frame that moves faster than the speed of light. But if they are massive, I can always go to an extremely fast-moving reference frame, so that neutrinos in that frame will appear to be moving in the opposite direction. So let's assume we carry out a large Lorentz boost. Yeah. Then after that Lorentz boost, as I said, by assumption, the momentum will now be backward. So let's call this P prime. The spin vector, of course, is unaffected by this large boost. So the spin will still be pointing backwards. So just by doing this large boost, I have turned my originally, I've switched the handedness of my neutrino. Originally, my neutrino was left-handed. Now it's right-handed after the boost. And I could only do this because I'm working with massive neutrinos now. So this is like an intuitive picture of why we now have to go from 2 degrees of freedom to 4 degrees of freedom. So in principle, we are done. In principle, we've now introduced neutrino masses. So in principle, we can now explain all experimental observations of neutrino masses. However, there's a more theoretical problem, and that is, if we look at these couplings here, if we look at the M alpha beta, then because we know that neutrinos are extremely light, we know that these M alpha beta must be very, very small. They must be much smaller than the masses that we are used to from the other standard model fermions. And that seems a bit unnatural or unusual, at least. Why should the masses of the neutrinos be so much smaller than the masses of the other standard model fermions? If you go from this effective description, we have just written down a mass term. If you go one level higher above the electroweak symmetry breaking scale, and you write this mass as a Yukawa coupling times a Higgs wave, because of course, by virtue of electroweak symmetry, this has to originate from a Higgs wave, then the question is, why is that Yukawa coupling so small? So let's see, oops. Let me write this down here. So this is a Yukawa coupling Y alpha beta times the wave of the Higgs field. And the question is, why is that so small? No problem. Why are M alpha beta so small? So it's not let's say an observational problem, but it's a theoretical problem to understand why they are so small. Now, one way of explaining why neutrino masses are so small is the so-called Seesaw Mechanism. But in order to understand the Seesaw Mechanism, we need another type of mass term, namely a Majorana mass term. So let's talk about Majorana mass terms. named after Ettore Majorana, who might also have been in the picture we saw earlier, I'm not sure. Majorana mass term. So the idea behind a Majorana mass term is we start from the observation where mass terms couple left-handed and right-handed fields. That's generally true. That's what they do. Mass terms couple left-handed and right-handed states. But now in principle, even without introducing the field nu r above, so the field consisting of the lower two components of a Dirac spinor, even without that, we already have a right-handed state in the theory, namely the antiparticle of the left-handed neutrino. So the antiparticle of nu left is a right-handed state. So the question is, could that right-handed state play the role of the right-handed neutrinos? So could nu r be identical? Identical to the antiparticle of nu left. Well, and if I ask the question that way, then obviously the answer is true. But note that what we are doing here, identifying the right-handed state with the antiparticle of the left-handed state, that works only for neutrinos, because neutrinos are massless. If I tried to do this with an electron, then, well, the right-handed electron carries a negative electric charge, whereas the antiparticle of the left-handed electron, which is a positron, carries a positive electric charge. So in that case, I can never attempt to do that identification. I would break the electromagnetic gauge symmetry. But for neutrinos, because they're massless, I can do this. Now we need to formalize this. What does it mean, the right-handed particle being the antiparticle of the left-handed particle? For that, we need an operation called charge conjugation. Or more formally, let's introduce the charge conjugation operation. Oops. Charge conjugation. So the charge conjugation operation maps a field psi to a field psi charge conjugate. This is indicated by a superscript C conventionally. And that is defined as -I times gamma 2, gamma 0 times psi bar transpose. And this whole thing here, this I gamma 2, gamma 0, this is sometimes just called the charge conjugation matrix 2. So notice that, okay, on the right-hand side here, we have some gamma matrices that ensure that the field has the right transformation properties. But notice we have here psi bar. So this contains the field psi dagger, right? Psi bar is psi dagger times gamma 0. So this contains the antiparticle fields now, where psi contains, for instance, a particle creation and an antiparticle annihilation operator. This field psi bar transpose contains a particle annihilation and an antiparticle creation operator. So it contains the charge conjugate field. And then the prefactors here are just there to make sure it has the right transformation properties under Lorentz transformations. Now, what does it do to chirality? So effect on chirality. Let's apply the chiral operator gamma 5 to the charge conjugate field. Right, gamma 5, the eigenvalues of gamma 5 are the chirality. If I have a left-handed field in which only the upper components of psi are filled, then this field transforms under gamma 5 with eigenvalue 1. The lower components transform with eigenvalue -1. Now let's see what happens if I plug in my definition of the charge conjugation operation. So we want to calculate gamma 5 times minus I gamma 2 gamma 0 times psi bar transpose. Remember that psi bar contains a gamma 0. That gamma 0 together with this gamma 0 here gives 1. So I just have there minus I gamma 2 times psi bar times psi star transpose, no, just psi star. The gamma 5 can be anti-commuted past the gamma 2. So the minus sign turns into a plus sign because of the anti-commutation. So I end up with gamma 2, gamma 5 times psi star. And I can write this as minus gamma 5 times psi and the charge conjugation operation applied to the whole thing. So what's happened is, if psi transforms under gamma 5 with eigenvalue +1, then psi c transforms with eigenvalue -1. So in other words, this operation indeed flips the chirality as we anticipated. So c hat flips the chirality. So it transforms a left-handed particle into a right-handed antiparticle. Transforms left-handed particle to right-handed antiparticle. And now we can say what we mean when we say we want to replace nu r by the antiparticle of nu L. So we now identify nu r equal to nu left charge conjugate. That's the basic idea of a Majorana mass term. So in 4-component notation, remember that the left-handed field was one where only the upper two components were non-zero, so chi1, chi2, 0, 0. Now, nu left charge conjugate is equal to minus I. Now, gamma 2 in this notation can be written as 0, sigma 2, minus sigma 2, 0. I should say that obviously I'm using here the chiral representation of the Dirac matrix, but that should be obvious from the way I defined my 4-component spinors. I've already factored in the gamma 0 here, the fact that gamma 0 cancels with the gamma 0 from the psi bar. So we have here chi star 0. And this can be written as 0, I, sigma 2, chi star. So that basically tells you also what the charge conjugation operation does in a 2-component notation there. Instead of gamma 2, it's sigma 2 that acts on the field. So this means we can now write our 4-component spinor. Our 4-component Majorana spinor now consists in the upper 2 components of the usual left-handed field, and in the bottom 2 components, where normally there should be 2 independent right-handed states, we now put in this I sigma 2 times chi star. And this is now what we call a Majorana spinor. Note that this spinor has the property that nu is equal to nu charge conjugate. But also remember that the Majorana spinor has only 2 degrees of freedom now, right? Even though it's a 4-component spinor, there's only 2 independent degrees of freedom, because we've identified the bottom 2 with the charge conjugate of the upper 2. And now this allows us to write down a new type of mass term. namely a Majorana mass term, which looks like the following. There's a factor of 1/2. You can call that factor 1/2 a convention, but if we use this mass term to compute the particle propagator and we want the pole of the propagator to correspond to the physical mass of the particle, then this factor 1/2 has to be there. So there is now this matrix M alpha beta, nu L alpha charge conjugate bar times nu left beta plus Hermitian conjugate. Okay. So we again have a matrix M alpha beta. However, now this matrix, it can be complex, but it has to be symmetric. This can be shown by looking at the transformation properties of this operator. So if we flip the indices beta and alpha, then it can be shown that the operator stays the same, and therefore this matrix has to be symmetric, but it can be complex. So symmetric, complex, 3×3 matrix. So now you might say, okay, we did a lot of effort. We introduced a new type of spinor. We introduced a new type of mass term, but the fact is still that neutrinos are extremely light, and we still don't understand where these numbers, M alpha beta, are coming from. And that's right, at this stage, we can't understand this yet. So first problem, why is M alpha beta so small? Same problem as before. And an even more fundamental problem. Does anyone see a more fundamental problem with this type of mass term? Think about, remember up here when we talked about the Dirac mass term, I explained how it can be obtained from an SU2 invariant theory, how it can be obtained from the Higgs. Does anyone see what the problem with this mass term is? Think about the symmetries of the standard model. What could be the reason that this mass term is even more problematic than a Dirac mass term when taken at face value? Okay, everyone is shy. Okay, well, the problem is that this mass term cannot be obtained from an SU2 invariant theory. So there's no way we can write this while respecting the SU2 invariance of the standard model above the electroweak scale. And that's because the electroweak symmetry dictates that everything that the neutrinos do, the charged leptons should also do. So if there is a mass term like this for the neutrinos, if it were there above the electroweak scale, then there would be a similar mass term also for the charged leptons. And I explained before that that's impossible because it would violate charge conservation. So it's not clear immediately how to introduce this term, but we can already say that we have to do some work to get it from an SU2 invariant theory. So how to obtain from SU2 invariant theory. And we're going to talk about that in a moment. So before I move to answering those two questions, do you have any questions at this stage already? This charge conjugation operation, it's a tough beast, so there's a lot of formalism involved here. So please feel free if you want me to go into detail a bit more on some aspects, if you have any questions, if you would like to make any comments. You can either write in the chat or just unmute yourself and shout. Otherwise, please feel free to.
Hello. Yes. So actually, I have read somewhere this this operator that you have told. I mean, this C hat operator. It is actually it is actually called the particle anti-particle operator and not the charge conjugation operator, because the charge conjugation operator, what it does, it changes the left-handed neutrino to the left-handed anti-neutrino, and it does not change the chirality. But I mean, you have shown here that that the way that you have defined it it flips actually the chirality also. So I am a bit confused that that means the definition of this charge conjugation operator in literature and the particle anti-particle operator in the literature. So can you please help me?
I think it's mostly a matter of how we call things. So in most of the literature on neutrino physics that I'm familiar with, it is called the charge conjugation operator, even though, I mean, the neutrino doesn't have, at least it doesn't have an electric charge. So if you apply the operator to a charged particle, like a charged lepton, for instance, then, well, it changes particle to antiparticle, but that also means it changes the charge, right? It changes we've seen that it changes a left-handed state into a right-handed state, but it also changes particle into antiparticle, because here let's see, where were we? Here, it contains psi star. So we transform psi into an object that contains psi star, so the antiparticle field. And therefore, I think both are true. It changes charge and it changes particle into antiparticle. Does that make sense?
Still, I mean, let us see. Suppose this, I mean, this C hat operator operates on this lepton field, say electron. So
Yeah.
I mean, will it change the chirality of the electron also, or the chirality will remain the same?
It will also change the chirality. It will transform a left-handed electron field into a right-handed positron field, if you wish.
Okay, then that is what I wanted to know. Thank you.
Yeah,
thank you.
That's what it does. So it sometimes helps to think about the expansion of these fields in terms of creation and annihilation operators, right? The field psi, it's not entirely correct to call it really a particle field or an antiparticle field, because the two cannot really be separated. The field psi contains an operator that destroys a particle, but it also contains an operator that creates an antiparticle. And similarly, psi charge conjugate contains an operator that destroys an antiparticle and an operator that creates a particle. In that sense, it's not really a good way of naming things by calling this a particle or an antiparticle field. The two cannot be disconnected from one another in the Dirac theory. And therefore, in the literature, one often talks about charge conjugation, because that's a bit more well-defined than particle and antiparticle. And it can be formalized here. The way we did this here with the effect on chirality, if you work in a theory that has a conserved charge like electromagnetism, then you can do a similar calculation by multiplying the charge conjugate field with the electric charge operator and showing that it also flips the sign of the eigenvalue.
Yeah.
Okay, any further questions at this point? Okay, then let's now finally talk about the Seesaw mechanism. Let's see, I'm at one, so this should be subsection 1.4 then. Oops. And we should not write so thick. We should write with the pen, not with the marker. So, oops. And I want to write in blue, come on. So here we go. So 1.4, the Seesaw Mechanism. I'll explain later why it's called the Seesaw Mechanism. So you know what a seesaw is. A seesaw is this toy which you have on children's playgrounds where while one end goes up, the other end goes down. And then you do like this. That's what a seesaw is. And the goal of the mechanism is, well, to answer those two questions. How can I understand that neutrino masses are so small, and how can I get a mass term from an SU2 invariant theory? So the idea is to augment the standard model with 3 right-handed neutrinos after all. So augment the standard model with 3 right-handed neutrino fields. In the context of the Seesaw mechanism, they are called NR rather than nu R, but their basic property is that they are singlet under the standard model gauge group. So they are singlet under all 3 factors of the standard model gauge group. Singlet under standard model gauge group. So for simplicity, I'm going to explain the mechanism now with just 1 left-handed neutrino and 1 right-handed neutrino, because it means I have fewer components to write down. So for illustration, consider 1 left-handed nu L, 1 right-handed NR field. And then the generalization to 3 flavors is straightforward. Now, let's look at the most general mass terms we can write down now. So we've already seen before that when we introduce right-handed neutrino fields, we can obviously write down a Dirac mass term like this, nu bar L and R. And the right-handed fields, now, if you look only at the right-handed fields, they are total singlets under the standard model. So this problem here, how to obtain from an SU2 invariant theory, does not exist for them. Well, because they don't transform under SU2 symmetry. So we will write down a Majorana mass term for them. There's no symmetry that forbids it, so we have to write it down. The coefficient here is called MM. And we write nu right charge conjugate bar times n right. Now, the Dirac mass term is assumed to come from a Higgs mechanism. So just in the same way that the other standard model fermions get their Dirac masses. And this implies, now since we want to understand why neutrino masses are so small, we don't want to make them small by hand. So we assume that this MD, this is roughly similar to maybe the Higgs mass, the top mass, the W mass. So let's write down for definiteness order MH, so order 100G. The Majorana mass here, well, it can be anything. It's a number we put into the Lagrangian. It doesn't need to come from any Higgs mechanism, so it can be anywhere. So we could imagine that it comes from some physics happening at grand unification or so. So we will assume that this can be very large. And by very large, I mean, for instance, of order 10 to the 14 giga-electron volts or so. So the first one here is the Majorana mass, the Dirac mass. The second one here is the Majorana mass. Now, this Lagrangian can be written in matrix form by making the following definition. So we define a vector n, which contains the left-handed neutrino field and the charge conjugate of the right-handed neutrino field. Right, the charge conjugate of the right-handed neutrino field is again left-handed, so this n still has reasonable transformation properties under Lorentz transformations. Now, with this abbreviation, I can now write the above Lagrangian as simply 1/2 times nc bar times a matrix M times n plus Hermitian conjugate. By the way, I should also have written down a Hermitian conjugate up there probably. So let me fix this. Here, there should be a Hermitian conjugate at the end. So this matrix M now looks as follows. This matrix has here 0, MD, MD, MM. It's simple to just multiply this out and see that what I've written here really makes sense. So we have -1/2 times nu left charge conjugate and right, both of them with a bar, times that matrix 0, MD, MD, MM, times nu left and n right charge conjugate. Now, let's diagonalize this matrix, right? It's an off-diagonal matrix, so the states that I've introduced here now, they are not states of definite mass, so let's diagonalize it. And in doing so, we are already going to use the assumption that MD is much less than MM. So we're going to assume MD is much less than MM. So I'm not going to do the diagonalization explicitly here because that's I mean, it's a standard linear algebra calculation. I encourage you to do it during the free study time today. What we find is that the eigenvalues are approximately, so in this limit MD much less than MM, we have one eigenvalue of order MM and one eigenvalue of order MD square, MD square over MM. And here you see already something, right? With MD much less than MM, this second eigenvalue here is now a number that is MD times a very small ratio. So this is now a very small number. So in a sense, starting from one mass term with a reasonable mass at the electroweak scale and one with a very large scale, we have dynamically generated a much, much smaller mass scale. And that's why it's called the Seesaw Mechanism, because we put one of the masses very, very large. We can do that because there's no symmetry that forbids it. And thereby, the effective mass of the other state becomes very, very light. So hence the seesaw picture. The corresponding eigenvectors are such that there is a field, let's call it NR prime. So that's the field after diagonalization, which is given by NR plus small corrections of order MD over MM times the nu L charge conjugate state. So in a sense, the eigenvector corresponding to this very large mass, it's almost identical to the NR field that we put in. So because that mass is so large, these fields effectively decouple from the theory. So they exist somewhere maybe at the grand unification scale or slightly below, but they do not affect everyday phenomenology. The second mass eigenstate, however, which we will call nu L prime, is given by nu L with only a tiny admixture of the original NR state. So those are the eigenvectors that correspond to the small eigenvalue. And those are the ones that are almost identical to the neutrino fields in the standard model, up to a totally unobservable correction. So these are going to be the fields that we observe in neutrino experiments. And these are the fields which now suddenly have become a very, very small mass. Okay. I should say there is one subtlety here, namely that there's one thing that I omitted so far. If you just do the diagonalization of this matrix, what you'll find is that there is a minus sign in front of this eigenvalue. So you may wonder, okay, what does this mean when I get a negative mass? Well, and the answer is that such a minus sign can and should be absorbed into a redefinition of the fields in order to make the masses that appear in the Lagrangian real. So this is absorbed by defining, well, nu L prime can be transformed into I times nu L prime. So in a sense, a factor of I can be absorbed into the definition of the state because an overall phase factor doesn't change the physics. And with that transformation, then the minus sign here is gone. This is just to warn you that if you do the calculation, you will end up with this minus sign, and then you need to know what to do with it. Okay. So that means that now the effective Lagrangian at low energy, the effective low E Lagrangian, now has the structure, there's just minus 1/2 md square over mm times nu L prime charge conjugate bar times nu L prime. And then plugging in numbers with md about 100 GeV and mm about 10 to the 14 GeV. We then get a neutrino mass of order 0.1 eV. So we've achieved what we set out to do. We've generated a mass term. We've even generated a Majorana mass term. It appears to violate SU2 symmetry, but because it's only an effective low energy theory, and we know how to UV complete it, we know that SU2 symmetry gets restored once these right-handed fields are reintroduced. And we've explained why the coefficient of that mass term is so small, in particular, why it is so much smaller than the mass terms of the other fermions, right? For the other standard model fermions, I can't do that because if I want to introduce right-handed fields for them, well, those right-handed fields have charge, so they can't have a Majorana mass term. So we have achieved our goal. Now in the last, let's see, I think I have ordered 10 minutes left, right, yeah. So in those last 10 minutes, I want to discuss a little bit how to measure neutrino masses. So that will then be 1.5, measuring neutrino masses. And I would like to introduce two ways of doing so. The first one are the direct kinematic measurements. Where the idea is that we follow the same strategy we follow for measuring the particles of other particles' masses. We look at their kinematics. The problem here is that neutrinos are much, much lighter, so it's a bit more challenging. So one typical decay here is the beta decay of tritium going to helium-3 plus an electron antineutrino. So the idea is that the maximum energy available to the electron in this decay, right? We can't see the neutrino, but we can see the electron. The electron has a maximum energy given by the Q value of the decay, where remember that the Q value, that's just the mass difference between the two nuclei. So that's M hydrogen minus M helium. Well, minus the neutrino mass. A little bit of energy has to go to the neutrino because the neutrino now has a mass. So the idea is to look for the kinematic endpoint, to look at the spectrum of electrons and see where it ends, if it ends exactly at the Q value or slightly below. So measure the electron spectrum, look at endpoint. The problem is that the Q value is 18.6 kilo electron volt. The neutrino mass is of order 0.1 electron volts. So we need to see a tiny deviation here. And that's what makes it so challenging. I'm going to show you in a moment, I'm going to show you pictures of an experiment that's actually trying to do that. But before that, let me also mention the second method, or one alternative method for measuring neutrino masses, namely neutrinoless double beta decay. I'm not going to mention cosmological neutrino mass measurements here because you're going to have a dedicated lecture on cosmology. But I should say that at the moment, cosmology gives the most stringent limits on neutrino masses. So what's the idea behind neutrinoless double beta decay? Well, you know what a beta decay is, but you may not know what a double beta decay is. So let's look at a series of nuclei which all have the same mass. So we're going to look at nuclei with the same nuclear mass number, but different nuclear charge. So I'm plotting here on the horizontal axis, I'm plotting Z. And here on the vertical axis, we plot the mass of the nuclei. And in this plane, a curve typically looks like, so here at the bottom, there is of course only discrete points because the nuclear charge of course is an integer. So a typical diagram may look like this. So you may not, what I'm trying to show here is that the nuclei lie on two different curves. This one here and this one here. The reason for this is that nucleons inside a nucleus always try to pair up. And so for nuclei that have even numbers of nucleons, every nucleon can find a partner to pair up with and form a particularly strongly bound two-nucleon system. For those nuclei which have odd numbers of nucleons, there's always one nucleon that can't find a partner. And that is energetically unfavorable, and therefore those nuclei have higher masses. So here the bottom curve, are the so-called even nuclei with even numbers of neutrons and even number of protons. And the top one are the even odd nuclei, where one of them has an even number, the other one has an odd number. I'm not showing odd nuclei here because they're like a proton doesn't pair up with a neutron so easily. Okay, now the decays that are possible here, of course, decays always go to a state of lower energy. So here we can, for instance, so this one here can decay into this one via a beta minus decay. But now this one cannot decay any further. So a decay to the next state is forbidden, but a decay down here is allowed. But this requires skipping one nucleus. So we have to convert two neutrons into protons at the same time. So this would be a double beta decay. And the same can also happen here on the other side with beta plus decays. So we are looking at a diagram where two neutrons are converted simultaneously into protons. Diagrammatically, this looks like the following. So we have here, from one neutron, we have a down quark converting into an up quark, emitting a W boson, and the W boson then goes into an electron and an electron antineutrino. And simultaneously, the same has to happen also for another nucleon. There's a second quark line here at the bottom with a down going to an up, and a W going to an electron and an antineutrino. And those two have to happen simultaneously. Now, the special thing is that for Majorana neutrinos, there is another diagram. For Majorana neutrinos, so remember that in a Feynman diagram, you can always, without changing the process, you can always replace an outgoing antiparticle by an incoming particle. Now here we have two outgoing antiparticles and no incoming particle. But for Majorana neutrinos, the particle and the antiparticle are identical. So there's the possibility of having the following diagram. There's again our two down quarks. going to 2 up quarks by emitting a W boson each. But now we connect the 2 neutrino lines. So we have an electron here, an arrow here, an arrow there. And here in between, that's where we have a neutrino mass term. That's where we have an insertion of the Majorana neutrino mass. And this diagram, which is by the way called a Lobster diagram, this is a diagram that only exists for Majorana neutrinos, right? I can't connect an outgoing antiparticle line to an incoming particle line if these are Dirac neutrinos, because then particle and antiparticle are just 2 different particles. I can't join their propagators. But for Majorana neutrinos, this is possible. And what you can also see here, we have here this insertion of the neutrino mass, right? The conversion from particle to antiparticle along this line has to go through the neutrino mass operator. So in other words, this diagram has an amplitude that is proportional to the neutrino mass. So in other words, by measuring the rate of neutrinoless double beta decay, we can measure neutrino masses if they are Majorana. So by measuring the rate of 0 nu 2 beta decay, we can measure neutrino mass, or we can measure Majorana neutrino masses. Okay, I see that it's essentially 11 o'clock. I still have a minute or 2, so I will still start showing you.
There's actually, Joachim, I see that there's a question in the chat that popped up right now.
Oh, then let's take the question instead, of course, yes.
Mihir, do you want to ask your question, or I can also read it out? I
can see the chat. I can see the chat. So the question is why odd double beta decay is not possible. Odd in principle should also be possible. The reason I haven't shown odd nuclei here is for them the energetics is a bit more complicated, because there we have an unpaired proton and an unpaired neutron. And usually I think protons only pair up with protons and neutrons only pair up with protons. So in those cases, we have 2 unpaired nucleons, so this should be energetically even more unfavorable. And basically, since I fixed my A here, for instance, if I have fixed, let's see, no, sorry, I think I made a mistake here. I'm sorry. Because I have fixed A, if I fix A at an even number, for instance, then the nuclei have to be even or odd, otherwise it doesn't work out. So the upper curve here should actually be called the odd curve. And the bottom one is the even curve, because they always have to add up to the same A, right? So they always have to add up to an even number. So it has to be even and odd. And so my argument should be corrected. So in the even nuclei, each neutron finds a partner neutron to pair up with, and each proton finds a partner proton to pair up with. And in the odd nuclei, there's 1 unpaired neutron, 1 unpaired proton. So 2 unhappy nucleons means energetically unfavorable, larger mass, and therefore the intermediate decays are forbidden, as I said. So thank you for that question. That has shown me that I made a stupid mistake here. So thank you for that. And I hope that also answers the question then, or is it still unclear?
I think, yeah.
Thank you. I see that Victor raised his hand. Victor Valera.
Yes.
You're echoing a bit. Normally Zoom should take care of that, but somehow it doesn't. So he writes in the chat that he needs just a second.
Hi, can you hear me better now?
Now it's perfect. Now I can hear you loud and clearly.
Okay, yeah, my question is related to the Seesaw mechanism.
Yeah.
The argument to add this MD and the reason why this MD is better than the small neutrino mass is because it's in the range of the standard model masses, right?
Right.
But then this means that this should be connected to the Higgs particle, and I don't see how this MD can be connected to the typical mass generation of the Higgs mechanism.
Yeah, I'm sorry, I should have been more explicit about this. So if you permit me to use this free space here to explain this. So at the SU2 invariant level, this would be an operator that comes with a Yukawa coupling, a left-handed doublet, this Higgs tilde field, which you know is I sigma 2 times Higgs star. This is this operation that moves the VEF from the lower component of the Higgs field to the upper component times NR. So this here, remember, this is I sigma 2 times H star. And so after electroweak symmetry breaking, this H tilde field is essentially 1 over square root 2 times the VEF in the upper component and 0 in the lower component. So it projects out the upper component of the doublet here, which is just the left-handed neutrino. Oh, sorry, it should not be an arrow, that should just be a bar. There is the VEF of the Higgs, and there's the right-handed field. And then the Y and the V together is what we call the Dirac mass. So by definition, this is MD times nu L bar and right. So this is how you obtain it from the SU2 invariant theory.
Cool, thanks. That answers the question, but now I have another question. So this
Please.
Lagrangian term would contribute to the decay of the Higgs?
No, because the right-handed neutrino is sufficiently heavy. So if these right-handed neutrinos were lighter than the Higgs mass, then the Higgs could decay into them. But in order to explain the smallness of neutrino masses, we need these right-handed neutrinos to be very heavy, or we again need the Yukawa coupling to be very small. So there's also versions of the Higgs mechanism where one accepts somewhat smaller Yukawa couplings in order to make NR lighter. But in that case, this Higgs branching ratio will be extremely suppressed. In the case that I've discussed here, where NR is very heavy, it can't contribute to the Higgs decays because it's simply heavier than the Higgs.
Cool. Thank you.
You're welcome. Thanks for the questions. I see another hand up by Shiva Sankar.
Joachim, can I make a suggestion?
Yeah.
We can, so in the interest of time, we can maybe break now and go into Gather Town.
Okay.
And maybe Shiva, you can ask your question in Gather Town. That should also be possible. Maybe we try this out. Yeah. Okay. I see. Thank you for agreeing to this. And then I would say we come back maybe 5 minutes later at 11:20 for the next lecture by Futili. So Joachim, if you have the time, it would be great if you could join us on Gather Town.
I should still be able to move over to Gather Town for like, it's anyway just 15 minutes. So I'm sorry for not leaving more time for questions in the end.
That's okay.
Okay.
All right. See you in a bit.
See you over there. Bye-bye.
And we are going to leave the Zoom room open in the meantime.